Okay, Ed and I are going to talk a little bit about contingent claims, AMMs today, and also we just wanted to quickly, thank everyone for having us attend this conference. It's so much fun. We came last year as well, and we always learn a lot and meet a lot of great people. So it's a great opportunity, and thanks again to everyone, all the organizers. Let me just jump right into the definitions here. So, like I said, we want to talk about contingent claims. AMMs. So first I'll tell you what a contingent claim is. Contingent claims are assets that give their owner a claim to a specific state-dependent payoff. So we can give a few kind of funny examples of this. One, maybe, so think of like a binary option. It pays off $1 if an event occurs and $0 otherwise. So maybe I want an asset that pays off $1 if the temperature in Miami tomorrow exceeds 90 degrees and $0 if it does not. Okay, so that's an example of a contingent claim. Of course, other important examples include put and call options. So, when we're talking about contingent claim AMMs, we're also kind of thinking about options AMMs. So, all of the logic can kind of be applied in the options case as well. So, before I repeat the word AMM again without defining it, let me do that. So an automated market maker is a protocol that quotes buy and sell prices for a particular asset without having to match buyers and sellers through a limit order book. So this is very powerful. It's kind of allows you to get predictable, deterministic prices independently of the market depth, what the order flow looks like. And there are some examples of automated market makers that have become, quite popular on chain for this reason, and we'll kind of talk about those a little more shortly. So then a contingent claim AMM is an automated market maker that quotes prices for contingent claims naturally. So the contingent claims AMMs, there are a variety of kind of specific considerations we need to make there. One is that the prices set by the contingent claimed AMMs need to be, so these are paid into pools that are used to fund the claims at expiration. So kind of in addition to the typical cash flow considerations you need to make when you're thinking about asset pricing, you also want to think about the ability of these proceeds to cover the liabilities at expiration. And this presents kind of a unique and very interesting challenge. And this is something we've been thinking quite a bit about. So we'll say more about that later. So before I dive too deeply into what the AMMs, what the kind of current state of the AMMs are, let's take a second to kind of map it to what the traditional market makers look like. So let's think of traditional market making in options. So traditional options market makers will have very favorable funding rates. Very, better collateral rates, often based on reputation and asset under management. So larger, traditional market makers will typically have better funding rates, more liquidity. So what you see in these markets is kind of a concentration, a small number of fairly large market makers that get very favorable funding rates. This does translate into some improvements for the traders who are using the system, because this translates into kind of tighter bid-ask spreads, faster execution, but it also puts the market makers in a position to extract rents from the traders. So, of course, it's well known these traditional market makers will have access to real-time order flow data. So kind of the canonical example of that is Robinhood, the relationship between Robinhood and Citadel. So Robinhood kind of sells and by the way, they just went public yesterday, it didn't go too well. So Robinhood kind of sells the order flow information of their traders to these high frequency trading firms that can then just kind of systematically front run the traders who are using Robinhood. And the market makers are kind of handsomely rewarded for being able to provide these services. So there are some things we can actually glean from the way that traditional market makers work that we would want to incorporate in a design of an automated market maker. And of course, we'd want to do that in a way that kind of prevents the rent extraction that's happening now. So, we want to think about how can we glean from traditional market making the things that they do right, without passing on the fact that they are extracting rents from the users. So one of the important things that traditional market makers do that we'd want to take into consideration for a contingent claim automated market maker is they hedge their exposure. So when they're taking on options liabilities, what happens is the so-called delta of their position can vary. And what they will be trying to do is hold roughly a zero net delta position across all of their exposures. And so in order to do that, as new option liabilities are coming into their system, they're often rebalancing a hedging portfolio that they have internally, taking on positions in the underliers in order to offset the delta exposure that arises from taking on the option risk. So when we're thinking about building options AMMs on chain, we want to be able to think about hedging the exposure in this way. So this is an important lesson we can learn from traditional market makers. Traditional market makers also are good at assessing particularly unhedgeable risk and charging a corresponding premium. Also, as I mentioned, some of the most successful market makers are very large and concentrated, so they actually have access to a large pool of capital, but also a fairly large pool of liabilities. And so they can kind of apply a law of large numbers when they're doing their statistical analyses. And this is also something that we want to be able to glean lessons from when we're designing an AMM for options on chain. So who are the basic players for a typical AMM currently? So I mean, it's always useful to think of Uniswap. So traders come in to, if you have a liquidity pool on Uniswap, traders will come in to swap one asset for another. That's one type of participant. The liquidity providers will provide both assets in some proportion in order to keep the pools liquid so that the traders can use it. And then there's a third, participant in these markets, arbitrageurs, and it's actually, I think kind of a mystery to a lot of people exactly what they do. So, why are contingent claim AMMs important? So, as we mentioned, contingent claims are, include things like health insurance, property damage insurance, financial options. These are all critical components of economic infrastructure. So, look, we can dig in a little bit to specifically the insurance case, actually, because this is something Ed and I think is quite interesting. And we don't really see much of this on chain yet. It produces really a unique challenge. But the current centralized methods for pricing insurance are, opaque at best. And the criteria for payment are often obscured. And specifically, they're often kind of modified ex post in ad hoc ways by humans with interests that conflict with the insured. So the insurance agent typically does not have the same interest as the insured, whoever the person is filing the claim. And so having a trustless AMM that can price contingent claims and maintain solvency when the claims come due, we think is a really important step towards implementing these types of systems in a trustless way, and then actually being able to use them to manage real world risk. So we think, these contingent claim AMMs, getting them working is something that could be really powerful. So quick discussion of what the current state of the AMMs are on blockchain. As I mentioned, Uniswap is kind of the most well-known one, constant product market maker. Noah gave a great comprehensive discussion on Monday about how this works. This is really nice for swapping on-chain assets because the quantities are observable. So you don't need to appeal to an off-chain oracle. You don't need to appeal to an oracle or off-chain computations in order to get the prices. The implication of this formula is that you just need to look at the ratio of the reserves to get the price, and all of that is available on-chain. So this is quite beautiful and very, very powerful. Balancer takes this idea and generalizes it to allow for mini assets rather than just pairs, and also allows it to, in the case of Balancer, you can also kind of apply heterogeneous rates of substitution. So if you want to think about the cost of adding or removing one of the assets in the pool being a little different than the cost of adding or removing another asset in the pool, you can kind of calibrate that with the exponential term. So, this is often called a geometric product AMM. It's also maybe a simple case of a constant function market maker. So a constant function market maker is something that keeps a specific trading function of reserve constant and then trades against that. And what's so an important channel along which this generalizes what Balancer has, for example, is you can accommodate non-constant elasticities of substitution between assets. So that's kind of a quick overview of kind of the state of where market makers are on chain and why we think contingent claim market makers are really, automated market makers are really an important thing to continue to make progress on. And with that, I'll let Ed kind of take over.
Okay, cool. Thanks, Patrick. So what are some of the drawbacks for constant function market makers for contingent claims? So it's actually interesting, but constant function market makers can actually replicate certain payoffs as payoffs to the liquidity providers, not to the traders, but to the liquidity providers. So in particular, it's been shown that constant function market makers can match concave payoffs, but only evaluated the current state. So that misses two important general contingent claim aspects of general contingent claim payoffs. They're often convex payoffs. Even in insurance markets, this is the case. You know, they'll have some regions of the underlier state where they pay off zero, and then others where they increase kind of linearly with damage, or in an increasing fashion with damage. It's especially true for options payoffs. Another problem, of course, is that contingent claim payoffs are fundamentally evaluated not at the current state, but instead at a future state. Next, please. So one potential kind of replacement, or one way to deal with this is by using hedging market makers. And this is inspired by a large literature in both academic finance and practice for derivatives markets. The most famous model for this is the Black-Scholes model, Black-Scholes-Merton model. And it's used by traditional market makers to create hedging portfolios when writing derivatives. Like Patrick talked about, this strategy involves constructing a portfolio of the underlier and risk-free rate to delta hedge. Traditional models assume that hedging portfolios can be rebalanced continuously. It's a very unrealistic assumption, so that's one of the drawbacks. Another drawback is that traditional models assume restrictive parametric models for the price process, and these bleed into how the construction of those hedging portfolios is actually done. Next, please. So what's one way to start to deal with some of these issues in terms of the infrequent, not being able to continuously rebalance, having trading costs, having markets that are incomplete and have unhedgeable risk? Well, one approach is to determine the indifference price, also known as the certainty equivalent of taking on a liability for an individual or for the general market participant. The indifference price of a liability is the minimum amount of money that is required to make an individual indifferent between taking on an additional liability or not. This accounts for hedgeable and unhedgeable risk. And it's kind of nice to see an expression here for what the indifference price is, so you can see what each of those components is. So here, on the right-hand side, what we have is an infimum over the allowable trading strategies. The delta is the trading strategy, and the H is kind of the set of allowable trading strategies. So sometimes you can't, for example, be able to trade in some of the underliers. The rho is the certainty equivalent function. L is your liability. And the second term there, the delta dotted with S, is your trading strategy. So that's to hedge, your hedging strategy. And then the C term is the how much costs are associated with that hedging. So basically, an individual will take into account the liability that they take on, how much they can hedge, and how much it costs in order to implement in terms of trading costs that hedge. So that's a little bit about how indifference pricing works and how we can incorporate that to deal with the unhedgeable risk. Next. So intelligent market makers, this is one way that we can go a little bit further. One of the problems in classical indifference pricing is that it relies on strong parametric assumptions on the distribution of the underlier, as well as the form that market frictions take. And there are ways in machine learning, in particular reinforcement learning, that we can relax this assumption. One of the very recent advances that's very promising on this is deep reinforcement learning. Next, please. So throughout this talk, we were mostly focusing on the pricing and how AMMs work for pricing, but it's also important to discuss what the role of LPs is in contingent claim AMMs. A few important ways that liquidity providers could contribute is they could provide funding for shortfalls in the hedging portfolios of the automatic market makers so that the law of large numbers can be exploited. They could provide insurance when hedging portfolios don't cover the full liabilities, and they could provide assets for arbitrageurs to trade against. In return, liquidity providers can get fees collected from the trading platform. Next, please. So what are some challenges? Well, one big challenge for more general contingent claim markets is asymmetric information and verification of damage, for example, in insurance markets. This is where trusted hardware might come in. But there's a whole host of privacy concerns there with how that might work. And we have some memes at the end if we have time. Next. So computational challenges are also really difficult. We have to be able to forecast. We have to be able to do things like Monte Carlo simulations, and these should be done off chain, at least for the current state of blockchain that exists. It's difficult to do these very, very highly computationally intensive calculations. So next, please. So how can we handle these off-chain computations? Well, we could use ZKPs, we could use SGX, we could use optimistic rollups. And there's kind of pros and cons with each of them. ZKPs have the issue that they're not built for kind of general continuous functions, but instead arithmetic circuits. SGX at least requires trusting the hardware. MPC might be a good alternative for that, where you don't have to trust the hardware as much. And then there's, of course, optimistic rollouts that have the 2 dispute period challenge for AMMs. Next, please. So yeah, in terms of just kind of wrapping up, again, when it comes back to the other challenges in general contingent claim markets, and doing things like having sensors or videos on your house for hurricane insurance if you live in Florida to determine the damage, we just wanted to kind of put up these funny memes that it kind of encapsulate how people might feel about having sensors all over their house with guarantees that they don't necessarily understand. Of course, the Linux one is great. But anyway, guys, thank you so much. If you have questions, I know we're out of time. Please feel free to kind of reach out to us on Slack, and we can answer any questions you might have. Thanks again to the organizers and to everyone participating.